Hi, I'm Greg Arnold, professor in Department of Surgery, also director of Smart Sensors and Integrated Microsystems Labs, where we do biomedical research from atomic level all the way up to the bedside. It's kind of, I have an idea, I can virtually design it, build it, do the physics, fluidics, optics, everything with it, integrate it together, create integrated circuits, do central nervous system implants to a number of other types of devices, and then to implement them, prototype, and implement them in the lab. The inertial measurement unit system was made for the Department of Defense initially. It's encrypted. It can pick up everything from your voice to 180 Gs, so extremely high. Because it's so broad range, we've adapted them to helmets for traumatic brain injury. I'll show you how we translate from a helmet information to a brain model for trauma, all the way to a blood test for trauma that we've done. But it's an example of a technology that is all encrypted, can hop around to all of these different things. We put them on robots, etc. We put them on surgeons where they mapped out the surgical motions that occur. So you're doing an interprecoral knot, for example, and being able to map that out and show augmented reality of how that's done, which is very difficult.
We can make any material that nature can make. Anything from sapphire thin films to diamond. An array of other ones, electroceramics, magnetics, magnetostrictive materials, but a whole lot of materials that nature can't make, like wide bandgap semiconductors and other things with electro-optical properties that are really unique. So here we start at the atomic level, and we do things a little different here. These are atomic physics instruments. This is Auger spectroscopy. It basically lets you knock off valence electrons, not valence, actually core electrons. And then you have an emission called basically an Auger emission. The Auger emission tells you what an atom is made of. So it's really, really good for looking at the atomic level, what something's made of. You can hit with ions and then do depth profiles. So what we have here are fractals. So the fractals we use with channels for nutrients to come in. And we looked at how to grow on these fractals in a bioreactor. And we found that if the fractals were very sparse, they just grew along like this. If they're really, really dense, they grow like a plate. But if they're just right, they grow in three dimensions. So we were able to grow both the breast model, we did a bone prostate cancer model, and we grow neurons in here in 3 dimensions.